City lights in the void, the James Webb Telescope's cosmic revelation. In the frigid void of space, 7 trillion miles from Earth, a golden marvel floats silently, its 18 hexagonal mirrors glinting faintly against the infinite dark. The James Webb Space Telescope, JWST, humanity's most advanced eye on the cosmos, has spent years peering into the universe's deepest secrets, distant galaxies, newborn stars, and worlds beyond our own. But on a quiet night in 2025, it captured something no one expected. Strange, shimmering lights on Proxima Centauri b, the closest exoplanet to Earth. These weren't the dull glows of volcanic activity or the fleeting flickers of auroras. They looked impossibly like city lights, a radiant suggestion of intelligent life glowing in the cosmic night. The discovery sent shockwaves through NASA's control rooms, university lecture halls, and the global scientific community. For centuries, humanity has gazed at the stars, wondering if we are alone. Now, with this unprecedented finding, the question feels closer to an answer than ever before. What could be causing these lights? Are they evidence of an alien civilization or a natural phenomenon we've yet to understand? Join us as we unravel the story of the JWST's discovery, the enigmatic world of Proxima Centauri b, and the tantalizing possibility that we may not be alone in the universe. Chapter 1. A Telescope Born of Dreams ***. The story begins with a dream, one shared by astronomers, engineers, and visionaries who dared to imagine a telescope capable of piercing the cosmic veil. Named after James E. Webb, the NASA administrator who championed the Apollo missions, the JWST was conceived as a successor to the Hubble Space Telescope. Launched on December 25, 2020, from a launch pad in French Guiana, it was a triumph of human ingenuity. Its massive 6.5-meter mirror, composed of 18 gold-coated beryllium segments, was designed to capture the faintest whispers of light from the universe's earliest days. Its instruments, near-infrared cameras, spectrographs, and a mid-infrared sensor, were built to see through cosmic dust and detect heat signatures from objects billions of years away. The JWST's mission was ambitious: to study the formation of galaxies, the birth of stars, and the atmospheres of exoplanets, worlds orbiting stars beyond our sun. But no one anticipated that it would uncover something as provocative as city lights on a distant planet. To understand this discovery, we must first journey to Proxima Centauri b, the exoplanet at the heart of this mystery. Chapter 2. Proxima Centauri b, the starlit neighbor. Proxima Centauri b, or simply Proxima b, orbits Proxima Centauri, a red dwarf star just 4.24 light-years from Earth. Discovered in 2016, it's the closest known exoplanet to our solar system, a rocky world roughly the size of Earth. But Proxima b is no earthly twin. Locked in a tidal embrace with its star, one side of the planet perpetually faces the fiery glow of Proxima Centauri, while the other is cloaked in eternal night. This stark division creates a world of extremes. Scorching heat on the day side, freezing cold on the night side, with a thin twilight zone where conditions might be temperate. What makes Proxima b so intriguing is its potential habitability. Orbiting within its star's habitable zone, the region where liquid water could exist, it has long been a prime target for astronomers searching for signs of life. But its host star, Proxima Centauri, is a volatile red dwarf, prone to violent flares that could strip away atmospheres or bathe the planet in harsh radiation. Despite these challenges, Proxima b has remained a beacon of hope for those dreaming of extraterrestrial life. Dr. David Kipping, an astronomer at Columbia University, has studied Proxima b for years. This planet is unlike anything we've seen, he says. Its infrared signature doesn't match the typical rocky planets we know. It's almost as if it's hiding something extraordinary. That something would soon come into focus, thanks to the JWST's unparalleled infrared sensitivity. Chapter 3. The Night That Changed Everything. In early 2025, a team of NASA astronomers huddled around monitors in a Maryland control room, analyzing data streaming from the JWST. The telescope had been trained on Proxima Centauri b, its instruments tuned to capture infrared emissions from the planet's night side, a region notoriously difficult to observe. Most telescopes struggle to detect faint light against the glare of a host star, but the JWST was built for this challenge. Its cryogenically cooled instruments could pick up heat signatures and light emissions 1,000 times fainter than starlight. As the data rolled in, something extraordinary appeared on the screens. Clusters of bright, steady lights emanating from Proxima B's dark side. The patterns were unlike anything natural. Neither the diffuse glow of volcanic activity nor the fleeting shimmer of auroras. They were organized, rhythmic, and eerily reminiscent of city lights seen from orbit on Earth. We sat there in stunned silence, recalls Dr. Elena Martinez, a lead researcher on the project. It was like looking at a photograph of Earth at night, but this was 7 trillion miles away. The team cross-checked the data, ruling out instrument errors or cosmic interference. The lights were real, and they were coming from Proxima B. Social media erupted with speculation, and headlines screamed, asterisk, city lights on alien planet? Asterisk, the discovery reignited humanity's fascination with the possibility of extraterrestrial civilizations, but also raised profound questions. What could be causing these lights? Were they artificial, or could nature itself be playing a cosmic trick? Chapter 4. Decoding the Lights. The lights on Proxima B defied easy explanation. On Earth, city lights are a hallmark of human civilization, electric grids illuminating urban sprawls, visible from space. Could Proxima B host a similar phenomenon? The idea seemed far-fetched, yet the data was compelling. The JWST spectrographs revealed that the lights emitted specific wavelengths, suggesting a source that was neither purely geological nor atmospheric. These aren't random flares or reflections, Dr. Martinez explains. The emissions are stable, patterned, and concentrated in specific regions. That's not something we'd expect from natural processes alone. One hypothesis is that the lights are artificial, produced by a technologically advanced civilization. The idea of alien cities, complete with glowing skyscrapers or sprawling energy networks, captures the imagination, but scientists are cautious. We can't jump to conclusions, says Dr. Kipping. Extraordinary claims require extraordinary evidence. The team began exploring alternative explanations, such as bioluminescent organisms or exotic atmospheric phenomena. Proxima B's unique environment offers clues. Its day side is bathed in intense radiation from its star, potentially powering vast arrays of solar panels or natural energy harvesting systems. On the night side, where temperatures plummet, any artificial lights would need a robust energy source. Could an advanced civilization have mastered energy production in such an extreme environment? Or might the lights be the result of chemical reactions in the planet's atmosphere, creating a glow that mimics artificial illumination? Lila imagined time as a river, but Cox's theory proposed that the river's flow wasn't absolute. Instead, it emerged in the interactions of countless quantum particles, much like ripples form on a pond disturbed by pebbles. In some quantum gravity models, time might not exist at the most fundamental level. Instead, it could be a construct our minds create to make sense of change and causality. This idea was radical, even unsettling. If time wasn't real, what did that mean for Lila's memories, her dreams, or her very existence? Cox's theory also touched on the arrow of time, the reason time seems to flow only forward, from past to future. Lila thought of her morning coffee, cooling on the table, or an ice cube melting in her glass. These everyday events reflected the second law of thermodynamics, which states that entropy, the measured disorder in a system, always increases or stays the same. A neatly stacked deck of cards becomes shuffled chaos. A tidy room grows messy. This relentless march toward disorder defines the direction of time. Cox suggested that the arrow of time might be more flexible than we think. In a universe where entropy could decrease, however unlikely, time might appear to reverse. Imagine a world where coffee leaps back into the cup or ice cubes spontaneously reform. Such scenarios are statistically improbable, but Cox's theory opened the door to exploring whether time's direction could vary under extreme conditions, like near a black hole or in the early universe. The implications were profound. If time is emergent, not fundamental, our understanding of reality could shift dramatically. Technologies like GPS, which rely on precise timing, might need new models to account for quantum effects at extreme scales. Space travel, already constrained by the speed of light, could face new challenges or opportunities if time behaves differently in uncharted regions of the cosmos. Lila imagined astronauts navigating a universe where time bends unpredictably, their clocks out of sync with Earth's. Cox's ideas also raise philosophical questions. If time is an illusion, what is the nature of free will? Are our choices shaped by a cosmic script written in quantum interactions? Lila felt a mix of awe and unease. The universe, once a clockwork machine, was now a tapestry of possibilities, woven from threads of space-time and quantum uncertainty. Gravity's enigmas beyond Einstein. As Lila delved deeper into Cox's theory, she couldn't ignore its roots in gravity, the force that keeps us grounded yet remains one of the universe's greatest mysteries. Einstein's general relativity described gravity as space-time's curvature, but alternative theories, like modified Newtonian dynamics, MOND, suggested gravity might behave differently in certain contexts, such as the outer reaches of galaxies. MOND proposed that gravity strengthens at low accelerations, potentially eliminating the need for dark matter, an invisible substance thought to hold galaxies together. Lila pictured galaxies spinning in the cosmic void, their stars defying Newton's predictions. Dark matter was one explanation, but Cox and others questioned whether it was necessary. Could gravity itself hold the key? Theories like MOND, while controversial, reminded Lila that science thrives on challenging the status quo. Einstein's relativity, once revolutionary, was now being tested against new ideas, just as Newton's gravity had been. Cox's theory also hinted at connections to dark energy, the mysterious force driving the universe's accelerating expansion. Einstein had introduced a cosmological constant to keep the universe static, only to call it his greatest blunder when evidence showed the universe was expanding. Today, dark energy resembles that constant, pushing galaxies apart and shaping the universe's fate. Cox's work suggested that time's emergent nature might be tied to this cosmic expansion, linking the arrow time to the universe's evolution from the Big Bang to its distant future. Lila thought of the Big Bang, a moment of unimaginable order when the universe was a hot, dense speck. As it expanded, entropy increased, galaxies formed, and stars burned out. This journey from order to disorder defined time's forward march. But what if the universe's expansion reversed? Could time itself rewind? Cox's theory didn't provide definitive answers, but invited Lila to imagine a cosmos where time and gravity were more intertwined than ever. The human experience of time. Back on her rooftop, Lila reflected on how these cosmic ideas touched her everyday life. Time wasn't just a concept for physicists. It was the rhythm of her existence. The ticking of her watch, the aging of her parents, the fleeting moments of joy and sorrow, all were governed by time's relentless flow. Yet, Einstein and Cox showed that time was malleable, shaped by motion, gravity, and perhaps even quantum mechanics. Lila thought of astronauts, whose missions highlight time's quirks. A journey to a distant star at near-light speed could age an astronaut mere years, while decades pass on Earth. The twin paradox wasn't just a thought experiment. It was a reality for future space explorers. Lila imagined herself aboard a starship, watching Earth recede, knowing that her return would thrust her into a future she could barely recognize. Even on Earth, time's relativity affects us. GPS satellites, orbiting at high speeds and weaker gravitational fields, experience time differently. Without corrections for both special and general relativity, navigation systems would falter, leaving Lila lost on her way to work. Time, she realized, wasn't just a cosmic puzzle. It was a practical force shaping technology and human experience. But why did time flow forward? Lila thought of entropy again. The shuffle of cards, the spill of coffee, the chaos of life. The second law of thermodynamics ensured that disorder grew, giving time its direction. Yet, Cox's theory suggested that time's arrow might not be absolute. In a universe with decreasing entropy, could time reverse? Lila pictured a world where memories preceded events, where the future shaped the past. It was a dizzying thought, one that made her feel both small and connected to the cosmos. The future of time. As Lila closed her book, the stars above seemed brighter, each a reminder of the universe's vastness. Brian Cox's theory, still in its infancy, was a spark of possibility, much like Einstein's ideas a century ago. It challenged Lila to rethink time, not as a rigid framework, but as a fluid, emergent property of a quantum universe. If time wasn't fundamental, What else might we misunderstand about reality? The consequences of Cox's ideas were tantalizing. Future technologies could harness quantum time effects, revolutionizing computing, navigation, or even space travel. Scientists might probe black holes or gravitational waves to test whether time behaves differently in extreme conditions. And philosophically, Cox's theory invited Lila to question her place in the universe. Was time a cage, trapping her in a forward march, or a canvas, open to new possibilities? Lila's journey through time wasn't over. She knew that physicists like Cox, building on Einstein's legacy, would continue to explore the cosmos, seeking answers to questions humanity had asked for centuries. What is time? Why does it flow forward? And what does it reveal about our place in the universe? As she gazed at the stars, Lila felt a sense of wonder. The universe was more intricate, more awe-inspiring than she'd ever imagined.